Welcome to the first quick tutorial from Line Between, and in this Houdini tutorial we'll be going over how to create procedural snow gather based on a geometry's normals. We'll keep this tutorial under 20 minutes and I hope you enjoy. In Houdini we can begin by dropping down a geometry node, and we can dive inside. And they actually removed the file node. That's something I never knew I needed, but it's great. So don't know how to do that. Let's place down a squab. We can drop down a transform node, and we'll just flip this squab over. So 180 degrees on the z-axis. And now we've got an upside down squab. So let's go ahead and drop down a bound. So bound creates a box around a geometry that perfectly fits. So we'll give this some padding. So one in each axis on upper and lower padding. So after the bound, we'll drop down a sort node. And what we'll do is we'll sort our primitive numbers from lowest to highest. So we'll say primitive sort by y. And if you switch on your primitive numbers, you'll see that the top one is now numbered 5 while the bottom one is numbered 0. So now we can go ahead and drop down a transform node. And we won't be using this right now, but we'll come back to it later. It'll just be used to define which direction our snow is coming from. So to kind of replicate wind. Now we can drop down a delete node. We'll delete non-selected by pattern, and we'll just say 5. So that deletes everything except primitive number 5, and there'll always be 5 primitives, and this will always be the top one. Because a bounding box will always have 6 sides, and counting from 0 to 5, it's 6 sides. So next we can go ahead and drop down a normal. And we'll change this from vertices to points. So all that does is it adds normal directions. So it'll just point up like that. Next we can go ahead and drop down a scatter node to scatter points onto this. So we'll be scattering a lot of points. And you'll notice that these points all gain normals. So that's great because we're going to be using that at a later stage. But for now, we will remove relax iterations and increase our total count to 250,000. So the scatter doesn't take very long because we're not relaxing the iterations at all. So it scatters points quite effectively. I mean, this is 250,000 points. It's quite a decent amount, but it just goes really quick without relaxation. So the next thing that we'll do is drop an attribute wrangle. And in this attribute wrangle, we'll just say v at dir for direction equals negative v at n. So now our direction will be the opposite of our normals, and if you remember correctly, our normals are facing up, so our dir vector will be pointing down. Next we can drop our ray node. Plug that into the first input, because that's what we're raying from. And plug your squab transform into the second input, and you'll notice nothing happened yet. We need to change this direction from to attribute. Instead of using n, we'll use dir. So now it's raying the points down, and the first thing that it comes into contact with, it will stick to. So what we'll do is create a ray hit group by saying create point group. That allows us to delete these extra points up here. So drop down a delete node, find your ray hit group, change this to points, and delete non-selected. Now we just have our squab. So now that we have some points, we would actually like this to generate some more points because these are quite sparse. So to do that, we'll drop down a pgen, point generate, and we'll use compute number of points. Now you won't notice the difference from the delete node to the pgen, but if you check how many points you have in your delete node, you'll see 30,000. If you go over to your pgen, you have 300,000. So we're creating 10 points per point at that point's location. And you won't actually notice it because they're all exactly on the existing point's location. So what we need to do is just jitter them. So this will fluff them up a bit. So a scale of 0.05 is fine. And now we just end up with this fluffy cloud of points, which we will ray again. This time we'll just be using minimum distance. So once again, grab your transform from your squab, and plug it into the second input of this ray node. Great. So now we have these points being rayed onto the surface. They've been fluffed up, so we have quite a decent number of points with an interesting density. So now the next thing that we can do is drop down a normal node, and we'll drop it onto the transform node coming from the squab. We'll just change it to points, and then we'll do a transfer attribute. Plug your ray into the first node and your normal into the second one, and we'll just transfer n. We'll do a distance threshold of 0.1, and now we can go ahead and do the wrangle. So this wrangle will control, density and the scale of our points. So in here, we can begin by saying float mult equals channel ramp, and then in here we'll say size, and it will be driven by a fit 0, 1. So fit 0, 1 fits a value between 0 and 1, and we would like our at n.y, so our y direction normals, to be fit between 0 and 1. Now we can create that parameter, and we end up with this. So we can continue typing, and let's bring up this string editor by pressing Alt plus E. Give ourselves some space. So next thing we'll be doing is saying float density equals channel float, and we'll just call this one density. Next we'll say float min equals channel float min mult equals, so now we're taking that mult value that we created. So currently mult is a gradient depending on the direction of our y normals. So if a surface is pointing directly upwards, then it'll be a value of 1. If a point is facing outwards away from the upwards direction, then it'll have a value of 0. So it'll make a lot more sense when I continue, and if you go to our blog post, because we have a lot of information there about how this is calculated. So next we can say mult equals fit. So fit is a bit different to fit 0, 1 in that it takes a value. So in this case we're going to take mult, and it takes the minimum, so 0, and the maximum of our existing value, and then fits it between a new value. So we're going to say for our new value min, comma 1. Next we can go ahead and say at cd equals mult, and that's just so that we can visualize this. So we can apply and accept and see what this looks like. So you can see the darker areas have a lower mult value, and the areas that are pointing directly up have a higher mult value. And you can adjust this, so drag this over, and you slowly lose those points in between. So now you can control, the density of the snow gather. What we'll do is we'll just set up a few points, and one at the beginning that is a 0 value. So now we've got a nice gradient between 0 and 1, and we can use that to generate snow thickness or whatever we need to do from here. And remember, you could also use this for dust, so perhaps these areas have thicker dust. So let's just go back into our wrangle, Alt E to bring it back up, and over here we'll say at p-scale. So p-scale is a generally used scaling value, and it's recognized by a lot of functions in Houdini and a lot of nodes. So for example, we'll be copying to points, and it will fetch that p-scale value and apply it to all points. So we can say at p-scale equals, and this time we'll go fit 0, 1. So firstly, we'll give it a random value depending on the point number, and we'll fit it between 0.01 and 0.035. So random value gets generated between 0.01 and 0.035 based on our point number. So each point has a different p-scale right now. Now we can multiply our p-scale at p-scale times equals, and we'll multiply it by our mult value. So now we have a random p-scale for every point, and it's multiplied by our multiplier, so those darker areas that you see towards the sides of the squab, those will have smaller points, while the top areas will have bigger points. Now I'm going to say if rand at pt_num, so if a random point, or if a point's randomly generated number between 0 and 1 is greater than mult times density, and do the following. Remove point 0, pt_num, sorry, at pt_num. And what that will do is take this density value. So say it's a value of 1, right? It will take our multiplier, multiply it by our density, and then if a point's randomly generated value is greater than this amount, then remove that point. So we're basically removing a percentage of points, because this will be a random value between 0 and 1, and there should be more or less an even number of randomly generated points of each value. So you'll see what that does shortly. For now, we'll just finish this up by saying at orient equals rand at pt_num. At spelling at pt_num. There we go. We can say vector direction equals chv, so that's a channel vector, in brackets direction. So before we close this off, orient, that's another value that's like p-scale, that's recognized by a lot of nodes and a lot of functions in Houdini. So orient just gives a orientation to an object. So we're saying give it a random orientation, so now all these points will kind of be rotated in a random direction. So we can say apply and accept, create our spare parameters. Let's push up this density. So as you can see, this works quite well. If we have a density of 1, then we have exactly what we started with. But if we bring this down, it lowers the density. Great. So we mess with our minimum value. So that basically controls the gradient. So a higher value means that there's thick snow everywhere, and a lower value just means that we have more of a smoothed off effect. So if you want really clumped snow, what you could do is perhaps push this all the way up, bring this up, and then increase the minimum, and you end up with really thick snow. But what we'll do is we'll drop it a bit, decrease our density a little bit, and just play around with this slide over here. And I think that looks pretty good. So now we can go ahead and copy to points. So drop down a copy to points node, and first input requires primitives, second input is the points to copy to. So we'll just feed the second input our points along, and then we can drop down a sphere. And the sphere we will change to a polygon mesh with rows of 5 and columns of 5. So that's how it looks now. And then we can copy to points. Now if you zoom in, we have all these spheres randomly oriented with varying p-scales. And so it's more or less done, but it would be a lot better to convert this to a VDB first, so that it smooths it off and we have nice geometry to work with. So what we can do is go ahead and drop down a VDB from polygons. Plug this into the first input. And before setting your display flag, you actually want to change something here. Set this to 0.005 and let this run for a second. It might take a while depending on your PC. But now we have this VDB that's been generated. And we can go ahead and convert that to geometry. So drop down a convert VDB, plug your VDB from polygons into the first input, and then change from change this from convert to volume to convert to polygons. Now we have some geometry that looks like snow. So now all that we have to do is maybe just add some noise. So we'll drop down an attribute VOP. VOP, there we go. Plug this into the first input. We'll dive inside here. So we can go ahead and drop down a curl noise and an add node. So this is generally how you would add noise to, positions and things. So we just plug our position into our curl noise position and our position into input 1 of our add node. And then our noise will plug into input 2. And then we can plug the sum into our p-value. And of course it's gone crazy because we have really high values on our curl noise. So what we'll do is we'll set our amplitude extremely low. We'll go 0.00005. And then for our frequency, we can push this up quite high. So we'll go 50, 50, 50, 50. And now we just have some general noise. And of course you can, I think, push this down a little bit lower. This seems a little bit too much. 2.5. And then we have that sort of bumpiness. Great. So we can jump back up and add a merge node. Of course, if you're rendering, you'd want to object merge this in and, do this in 2 separate nodes, but this is just so I can show you what this looks like. Bring down your squab transform, plug this in here, drop down a normal, and there we go. So now we have the squab that has snow gathered on its surface. So now, what if you don't want the snow directly, coming from the top? Let's say we want to replicate some sort of wind where it's been coming from the side and it's been hitting the side of the squab. Well, that's what we created on this attribute wrangle, that vector direction. So just set your display flag back onto your attribute wrangle. And what we'll do is we'll copy parameters. So right click on direction, say copy parameter. And we'll go up to this transform node after our sort. Remember the one that we placed where we didn't actually change anything? So over here we can say paste relative references, and now if we go onto this attribute wrangle and say change our z direction to 45, we now have snow coming from a direction of 45 degrees. So the snow is coming more or less from here, and you can see that by setting your display flag onto your plane that we generated. So it's raining it from the side. And we can go ahead and do all those things that we've been doing before. So there you have it. Our first quick tutorial, just going over how to create this gathering effect. So, snow collection or dust or whatever you need this to be for. And if you'd like to see more things like this, please go ahead and leave a comment down below and we'll get back to that. Also, if there's any effects that you'd like to see us do or recreate, then go ahead and drop a comment. If you like what we do, please subscribe, like our Facebook page, and we'll be back soon with some really cool things. And yeah, hope you enjoyed.